Welcome back to Physics 152 Online. We would like to make an analogy between Gauss's law for electricity or electric fields and then a similar equation for magnetic fields. And we call this Gauss's law for magnetism. And it turns out that the form that we have for this equation in magnetism is much simpler than it is for electric fields. And the reason for this is, to the best of our current knowledge, magnetic field lines always form closed loops. In other words, there's no such thing as an isolated north or south pole. And as a result, even though we draw magnetic field lines coming out of a north pole and going into a south pole for a magnet, the field lines actually continue all the way through the magnet itself to form a closed loop. And so, remember, for Gauss's law, what the expression was telling us was that when you have an electric flux, which is a measure of how many field lines pass through a particular surface, and a very special kind of surface is a closed surface. The electric flux through a closed surface was always equal to the charge enclosed by that surface divided by the constant epsilon zero. And that was because electric fields begin on positive charges and end on negative charges. And so if you had a net charge inside that closed surface, there always would be a net flux, because field lines, you'd have potentially more field lines going out than coming in, or vice versa. But if what I've just said about magnetic fields is true, then the magnetic flux through a closed surface, even though we write it down the same way as the integral of B dot dA, where B is the magnetic field vector and dA is the normal vector to the surface, when that's written down for a closed surface, when that's written down for a closed surface, the answer is zero, because there is no such thing as a net magnetic pole. You can never have just a single north pole or south pole. So this always has to be zero. And it's simply telling us a statement about the nature of magnetic fields. Now, I do want to say, even though this equation looks very trivial, almost as if it wouldn't have any importance, we still can calculate the magnetic flux through a surface that's not a closed surface. For example, if we just had a planar surface and a magnetic field in that region of space where the field lines pass through it, we could calculate the magnetic flux through that surface. And if it's not a closed surface, the answer would not be zero. And it will turn out in our next section of the course that we will often need to calculate the magnetic flux through a particular surface. So we'll come back to this kind of an expression in a little bit. But for now, I'd like to make the transition to the next section where we make the jump into where magnetic fields come from. Because if you think about what we've done up till this point, although we have talked a little bit about bar magnets, we have never written down anything formal about where magnetic fields come from and how we could produce a magnetic field of a particular strength. So the history of this was that not too long after it became possible to create electric batteries that could produce steady electric currents, a Danish physicist by the name of Hans Ørsted discovered, as I understand it, quite by accident, that an electric current through a wire caused the deflection of a compass needle. And so that was the first indication that electric and magnetic phenomena were one and the same, or at least were very closely related. And the interpretation was that electric currents, moving electric charges, are the source of magnetic fields. And within a year, by 1820, two French physicists, Jean-Baptiste Biot and Biot-Savart, along with Andreas Ampere, determined the quantitative relationship between electric current and the magnetic field that it's produced. And in the modern form, here's how we write it down. Imagine that you have a wire that's carrying a steady current I. And then, somewhere along that wire, we just draw in an infinitesimal vector, dl, that's along the length of the current. And there's an expression that tells us the contribution that that tiny amount of current has to the magnetic field at a certain point in space. So we pick a point in space, call it P1 over here. We draw a vector from the location of the current element out to P1, and then we form the cross product, dl cross r. And that cross product points in the direction of the magnetic field that's produced. So you can see by using the right-hand rule that at point P1, that magnetic field would point down. So the magnitude of the magnetic field produced by the entire wire would be what we get when we integrate this quantity all along the length of the wire. So it's I times dl, and you make the cross product with the r hat unit vector. The unit vector points along the direction of this vector r, but it, as its name implies, it has length equal to 1. It's a unit length. And so then you divide by the magnitude of that distance squared, magnitude of that vector squared, and there's a constant mu naught that plays the same role for magnetic fields that epsilon naught does for electric fields. And this now is a vector quantity that we integrate or add up all along the length of the wire carrying the current. And that will give us the net electric field at a point P1. So notice that this magnetic field will be different depending on where we're trying to calculate it. If we were to calculate the magnetic field due to this current element at point P2, we would get a very different result. And you can check out using the right-hand rule to find out what the magnitude of that magnetic field would be. This equation is called the Biot-Savart law. And in particular, when you're integrating something, when we integrate something and that gives us the net result for the magnetic field, the quantity that we're integrating is the infinitesimal magnetic field dB. Notice that this is a vector, and this is the first time that we are actually doing the integral of a quantity that's a vector. And we have to be careful when we do this, because as we move along the length of the wire, it's possible, in some cases, that the direction of that vector might change. Although for the simplest problems, it doesn't. Notice too that the proper pronunciation is Biot and Savart, the Biot-Savart law. And I just want to use this to do one very simple example. It's a very, very simple case, but it's a powerful application of this new principle telling us how to calculate magnetic fields produced by currents. So imagine that we have a circular loop of current. Don't worry for the moment about where the battery comes from that's supplying this current. Maybe there's a very small piece of wire. We cut this loop, and then the two wires from that opening go out to a battery. So imagine that if you're worried about how you would do this practically. But imagine that you have this ideal circular current loop, and we want to find the magnetic field at the center of it, where the loop has radius r. So we're going to use the Biot-Savart law, but first we need to find the dl cross r term. And so if the current is flowing in this sketch in the counterclockwise direction, the dl vector at the very top of the ring points to the left, the r hat vector points downward toward the point where we're trying to find the field, and you can see with the right-hand rule that dl cross r hat will be in the positive x direction. And one of the nice things about this is no matter where you are along the wire, let's say that we're at the bottom of the wire, the dl vector would point in the negative z direction, the r hat vector would point in the positive y direction, and forming the right-hand rule, forming the cross product of those two, would still give a cross product along the direction x, along the I hat direction. And so no matter where we are along this wire, dl cross r hat would give the same result. And the magnitude is easy because for a cross product you take the product of the magnitudes of the two vectors. dl has magnitude just dl, differential length. R hat, since it's a unit vector, has length 1. The angle between them is 90. Sine of 90 is 1, and the direction is in the I hat direction. So this cross product simply gives us dl times I hat. Now we plug into the Biot-Savart law, mu naught I over 4 pi. Those are all constants, and they come outside the integral. And now we're integrating around the loop. The numerator gives us dl I hat. The denominator, all that's left is the distance squared, and the distance from the current element to the point where we want the field is simply the radius r. So that r squared term is also a constant, which can come outside. And notice all that's left in this integral. It's still a vector integral, but all along the length of the loop, every point gives us a contribution to the overall vector that's in the I hat direction. So all that we really have to integrate is the entire sum of the lengths dl as you go all the way around the loop. And it's pretty easy to see that that's nothing more than the circumference of the circular loop, because 2 pi r is the circumference. Once we plug that in, we get a very, very simple result. Mu naught times I over twice the radius in the I hat direction. And this vector integral became simple because all of the different parts along the loop were all pointing in the same direction. And so it was a very simple integral to do. So this result is an important one. It's obtained by the Biot-Savart law, and we will go on to do some more examples showing how the Biot-Savart law can be applied to find the magnetic field due to other shapes of current loops or current lengths of current. Hope that's been helpful, and as we do some more examples, I think that the use of the Biot-Savart law will become a little bit more clear. I'll see you in class.